So, how you guys doing today? Good, perfect. At least it's Friday, right?
Yes.
Perfect, yes. So, let's, it's a good thing. So, I'll move on to the next part from what we discussed on Wednesday. But just a quick review here though. So, change in energy, we said determined by the amount of the heat energy, which we represent as a Q, and also W here, which represent the work. Okay? So we did a lot of practical problems together with this one. If heat is going in or going out, if we work done by system or deciding to do this work for the system, it'll be plus and minus, all we did on Wednesday. So from here, there's additional one I want to discuss from this one is the here. So this is kind of tricky. This word is equal to negative P delta V. Okay, so this here P stands for pressure. Pressure. Okay, and then this V stands for volume. Okay, volume over here. Okay, so this is here. So we just multiply pressure by the change in volume, and also the negative side will be this one. So I'll explain why this is in this way. Okay. So try to remember this one. Okay. So here's the thing. Like I said, if system does work, means it's negative, right? Because there should be. I'll give you some number to be very clear. So if system does 100 joule amount of work, then that means it's negative because to do the work, they need to spend the energy. So that's why the system lost that amount of energy. So it's negative 100 joule for the work here. So for example, if we had the cylinder here, okay, and this is plunger here, and you have a system right here. Okay? You have a system right here, and then let's say we have a system doing a work to the surrounding. So everything else is surrounding right here. Okay? So if the system, like it says, does work, so then they're gonna push the plunger here, so they can be actually do the work. Okay? So we'll do the expansion, right? Because when the system does the work, the volume will be increased. Okay, so maybe it didn't work, so maybe move to here. Okay, move to higher position here. Okay, so meaning maybe this is 1 liter, this is 1.2 liter, for example. So it pushed the plunger here in the cylinder, so your final volume has been increased from the initial one. So let's try to do this one for the moment here. So if the delta means change in something, so delta V is change in volume. So this is a change in volume. Okay. And then it's always the same. Like we did for the change in temperature, it is going to be volume, final volume minus initial volume. Okay. So you have now the change in volume, right? So it's the final volume minus the initial volume here. So if you do this one over here, the final volume is 1.2 liter because it did expansion, minus the initial volume was about 1 liter. Okay, so the change in volume will be what? 0.2 liter. Okay, so if that change in volume times by pressure will be the work here. So maybe here. But if you do this one over here, this positive number times positive pressure here will make a positive number here. But it has to be negative. So we put the negative sign. Okay? So I'll do this the other way. It makes more sense. So let's say we have a 1.2 liter initially. So now this is the initial volume here. Okay, and then I press this one. So Either we try to press this system in the cylinder, so it actually contract. It's like a compressed down to 1 liter. Okay. Here. So that means the surrounding, which means any one of us or anyone except the system, did work to the system, right? Makes sense, right? Yeah.
So we did it?
Yeah, we did it. Well, anybody except the system. So surrounding means anything except the system. Yeah. So it could be you, me, or anything else did a work to the system, meaning system will get this amount of energy. So if it was 100 joule, they got this much of energy here. So that will be positive. But here's the problem here. The final volume is 1, but minus 1.2, which is initial volume, will be negative. So negative 0.2 times the pressure will be the negative number. But it has to be positive because system actually gained energy. So it did actually put the negative sign because you have to look at this from the point of what? System. Does it make sense? Okay. So okay. So the technically, this is only. I did it only for the understanding, but what you really need to know for the exam is this one. This one, okay? So work is equal to negative sign, with the negative sign, pressure times change in volume. So product of the pressure, yeah. So this will be the something that we can use here here. So if we have this one, this will become really important when we talk about the enthalpy. So enthalpy is once again, this is the heat energy equal to the energy, internal energy plus product of the pressure and volume over here. Okay. So in this case, I don't know if you guys remember this. Enthalpy or internal energy itself is really hard to estimate because of its nature. But it's always easier to get this one. Okay. Change in something. So what I just did over here is instead of getting each enthalpy or energy or the pressure and volume, we wanted to make the number for the change in enthalpy should be equal to change in energy plus the pressure times change in volume. So in this case, we fix the pressure over here. So we fix pressure over here. Okay? And then what I'm gonna do here is do you see this one over here, right? The change in energy is equal to Q, which is the heat energy plus work. Okay? So I'm gonna copy right here. Okay? So if I do this one, this one, okay? Make sense, right? Okay. And then what I'm gonna do is I'm gonna move this one because this is same as work. I'm gonna put it here. Okay, so then it will become what? Negative pressure times change in volume. Okay, make sense, right? So then, do you see this, the negative and plus? So let's cancel. Right? So the change in enthalpy, so not enthalpy, but change in enthalpy, is the same as your heat energy from your system at constant pressure. Because we fix the pressure, we only changing the volume. So if that is the case, that the amount of heat energy is either released or the gain into the system should be its enthalpy change of the reaction. If it's happening at the constant pressure. there's no change in pressure, just measuring the how much heat energy either coming out or going in should be the same as the enthalpy change of that reaction as well. Okay? Does it make sense? Okay. So the all right. Okay. So the here's the thing. Whenever we talk about the change in enthalpy now, okay, if that is the negative, meaning they lost the heat energy, right? They lost the heat energy if it's happening at constant pressure. So that means they lost the certain amount of energy, right? Heat in form of a heat. So meaning the system, if there's a system losing the amount of heat energy, meaning it's going out. So heat energy now here is going out from the system to surroundings. Okay? So that's why it's a negative sign, because they're losing energy by just giving up the heat energy to outside. So for point of the system, it's negative. Makes sense, right? So we call this exothermic reaction. So the key point here is you have to look at this one as from the point of the system. Okay, so then all makes sense. This will become negative because they're giving off the heat energy to outside, the surroundings. So they're losing amount of energy, which is negative sign. And then we call this exothermic reaction because thermic simply means there's some sort of a heat-related problem there. Exo means it's going out. So the point is where it's coming from. It's from the system, but it's going out outside of the system. So it's losing it. Okay? If that is a positive, it's opposite, right? They're actually gaining the energy, heat energy, right? So meaning, if you have a system in the surroundings outside, we're actually putting heat energy into the system. So we actually putting the heat energy into the system there. So this will have a positive sign because of that, because they're gaining energy here, and we're gonna call this endothermic reaction. Okay. So endo means it's going in. This is mainly what we're gonna discuss in this chapter, one of the main parts of the chapter 5. So obviously, a good example of exothermic reaction, most famous example would be combustion reaction. Okay, combustion reaction. So if you're burning something, eventually the system, which means in here, is combustion reaction system. So if they do this one, combustion reaction, which is kind of really fast oxidation, and then going to be carbon dioxide and water here. So this whole system is now our system. So this chemical reaction is our system, and they're going to give us heat by doing combustion reactions. So this is so combustion reaction is a really good example of exothermic reactions, because we're gonna get lots of heat energy from the chemical reactions, which our system giving us lots of heat energy. So that's why whenever you have a combustion reaction, you feel hot, meaning you're actually getting heat energy from the system. That's why you feel hot, because it's a heat energy. Okay. Makes sense, right? Okay. So how about the endothermic reaction? So endothermic reaction is we actually giving the heat energy, right? So if you look at the cold ice pack, some of them is ammonium nitrate. So when they go into the water, so when you click the button in the ice pack, they will break the package, and they will be slightly being dissolved in water. Okay, and then to do that, so there will be, so when they become dissolved in water, meaning is they're ionized. So these two will be in cat ammonium cation plus nitrate anion. Okay, so gets now in water. So there will be an aqueous phase. So when they're being dissolved in water, they need to have energy. They need to have a heat energy to do so. That's why if you touch the cool ice pack, you feel cold, because they are stealing heat energy from you, which is your part of the surrounding. And this is a system. They're going to steal the heat energy from outside. So this is why it can be used for the cool ice pack. Okay, makes sense, right? Perfect. So now we know how you can use the enthalpy change. Not just the enthalpy, it will be so hard to get, but change in enthalpy might be easier to, compared to the enthalpy itself. So we know there's exothermic, endothermic. Then the problem is then how are you gonna find out if that chemical reaction is going to be exo or endo? That's the problem now, right? So to do that is that there are mainly two ways, but the first one is like this one. So we have, so on your exam, I'll give you a table, which is for enthalpy change of formation. So meaning, if there's any the chemical compounds or elements going through the chemical reactions, they'll be all listed on this table. For example, it's A compound, B compound, and C compound, and D. Okay? And then what I'm gonna do is I'm gonna show you the chemical reactions. So maybe A plus B makes C and D. We actually gonna do the practical problem soon, but just this is a basic rule. So this is on the left side is your reactants, right? The reactants. This is your products. Okay, and then what I'm gonna do is this is enthalpy change of formation, which can be measured at 25 Celsius degree and the 1 atm, which is also you can see as a fixed pressure. Kind of makes sense. So here maybe we can say this is -10 plus 20, 15, -20. Okay, so you can do this one over here. So you have something like this. I'll give you a specific example soon, but this is how we're gonna do it in this format. So enthalpy change of the reaction, I'm just gonna put Rxn, the reaction, should be equal to the sum of products, their enthalpy change of the formation, minus sum of the reactants, their enthalpy change of the formations. Okay, so in this rule, what you really need to do is this is the products on the right side, the reactants on the left side, and you find the compound name on the table that I'll give you on the exam too. And then there will be some number on the enthalpy change of formation. And then it says the sum, so you have to add them all. Okay, so meaning you have a two product, which is C and D, is right here. Okay, so C is a 15, D is what? -20. So 15 plus -20 is -5. Okay, it's -5. And that whole thing minus, you have to do sum of these two, so the A and B is right here, which is -10 plus 20, okay, over here. So then this will make 10, right? -10 plus 20 is 10, right? So -5 minus 10 is what? -15. So meaning enthalpy change of this reaction is negative. So whenever I do this one, this will be exothermic reactions, because they're going to release the heat, which means the system will lose the energy in form of a heat. So this will emit the heat to us. So this will be exothermic reactions. Okay, so this is the how we can get them. Does it make sense? So let's try to do something more. So let's say we have a coefficient number for this reaction here. Maybe it's a 2, this is just 3, maybe this is 1, and this is a 4. Okay? So we have not just 1, 1, 1, 1. We have a coefficient number for each reactants and the product here. And here, you're just gonna do the same thing. You just basically gonna do the same thing, but whenever you have a coefficient number, you find this number on the table and multiply that number by its coefficient number and do the equation. Okay, so in this case, what I'm only going to change here is, so this is the C and D, A and B, right? So C was 15, but C was only 1, so you don't have to do anything for this one, okay? But D was what? Negative 20 here, but there's 4. Okay? So then I'm gonna multiply this negative 20 by 4. Okay? So then these two will make what? 15 plus negative 80. Okay? So in sum will be what? Negative 65. Okay? Makes sense, right? Okay. So same here. So I'm not going to change it much, but just the number here. So A is 2, but it's negative 10. So here's negative 10. I'm going to multiply by this one by 2, because it's 2 right here. So this will become negative 20. Okay. And then this is B is 20, but this is by 3. So I'm going to multiply this 20 by 3. So this will become 60. Okay. So negative 20 plus 60 is what? 40. Okay, right? 40. So in this case, you have a negative 65 minus 40. So that will become negative 105. So this will be still what? Exothermic, perfect exothermic reactions. If you're getting this number somehow, for example, like plus 1 or plus 10, that means that reaction will be endothermic reactions. It's not actually going to steal the energy from outside. Okay? So we'll be getting, yeah. All right, so let's do a practical problem here. Does it make sense so far? Is it good?
So if it's negative, it's exothermic.
Mhm.
And if it's positive.
Perfect, that's it, yes. There you go. Perfect. Very good. All right, so I'll give you here, let me give you one example here. Okay. Okay. So this one is the obviously combustion reaction, right? So this will be 2, there'll be 4 and 8, so it'll be 4. So in this case, oh, was there a question? Oh no, okay. So there'll be 2. So you see there's 2. I just put 2 here because there'll be 2 carbons, 4 by 2. So it'll be 4, and there'll be 1 by 4 is 4. So to be in total 8. So in this diatomic molecule has to be 4. Okay?
So
Yeah. Wait a minute, just 1 second. 8. Oh, sorry. So there will be oxygen here too, because this is not the organic compound with the hydroxy group. So this will be 3, because this is in total 8, but it already has 2 over here. So we only have to have 6 for this one. So it'll be 3. So anyway, if we have this chemical equation here, I'll probably give you some number for enthalpy change of the formation. Okay. And this is something I want you to remember. This will be always 0. So enthalpy change of the formation of the O2 is always 0. And this is about, okay, and this is about the 2, 4, 9. Maybe I should double check. This is the, oh, 1. Yeah, so if you have this one over here, what you're going to do is same. So this is your reactance, and this is your products over here. Okay. So only thing you have to do is this number and this number together. But like I said before, if you have a coefficient number, make sure you multiply that enthalpy change of formation by its coefficient number will be 2, and be 4, and add more. Okay, and then minus. So I'm gonna do maybe right in the below. Two. Okay, over here. And then this is the sum of the product, right? Because it's under this side. And minus sum of the reactants over here, which we don't have to worry about this one, but just this one because this is a 0. But there's a 2, so it'll be 2 times -2 and 6, 6. Okay, so if you do that all together, that is your enthalpy change of the reaction right here, okay? Which will be about negative 1279. But which you have a negative sign, obviously kind of makes sense because this one has to be exothermic reaction. It's a combustion reaction. So even though you do the calculation, you're expecting some number with a negative sign. If it doesn't, you made a mistake somewhere in this long process of the calculation. That's what it means. But this should be so. But this is how we can get the enthalpy change of the reactions using enthalpy change of the formation of this reactants and the products and sum of the products by its coefficient number minus the reactants. Okay. Does it make sense? Okay, we follow the same rule, but here's so let's try to do one more. Okay, let's do a bit more. Okay. Okay, maybe. Can you guys have another one here? Okay, can you guys do this one? Okay. Okay, this is pretty much the same. Okay, this is 84. It's 84, yeah. And this is 0. Okay, so this is an enthalpy change of formation for each. And then maybe you can try this one. We'll do this together in 3 or 4 minutes. It takes quite a time. The first thing what you need to do is balance. So you need to balance the equation. So you know what coefficient number for each you need to have for calculations. And then if you do sum products minus sum of the reactants will be the answer for enthalpy change of the reaction. Oops. Okay. About 3 or 4 minutes, it takes some time. Okay. It's a long process. Okay. Oh, sorry. Negative. Okay. Okay, about 2 or 3 minutes, we'll do this together. Okay, 1 or 2 minutes, we'll do this together. So it's try to balance the equation first and do sum of the products minus sum of the ring. But make sure you do multiplication of your enthalpy change of formation number by its coefficient. That's why you need to balance the equation first. Okay, about 1 minute, we'll do this together. Okay, 20 seconds. All right, so let's try to balance the equation first. What you can do is you can normally always start with the 1 here. So you can try to simplest number you can think of is 1 here. And then to get 1 here, you need to have at least 2, because each ethane has 2 carbons here. So that carbon dioxide has only 1, so that's why you have to put 2. But to have a 1 ethane, we'll have 6 hydrogen here. So I'm gonna put 3. So each water has 2 hydrogen there, so it makes 6 there. Then if you go now, it will be 2 times 2 is 4 oxygen on here. 3 times 1 is 3 oxygen over here. So that makes the 7 oxygen on the right side. To get the same numbers on the left side, it has to be 7 over 2, because it is a diatomic molecule. So you can also do this one here, but you try to multiply by 2 to remove the fraction number. Then you can do 2, 7, 4, and 6. Okay. So all right. So if you do this one over here, what you can do is this number times by 4, this number times by 6, all together, minus this one. So what I'm gonna write here is 4 times negative 393.5 kilojoule per mole. Okay. Plus 6 times negative 241.8 kilojoule per mole. Okay. So this is the your product, sum of your product, right? Minus, so this is not gonna affect much because it's 0, but just minus 2 times negative 84.7. Okay. And that is your answer right there. Okay. So once again, obviously you're gonna have some big number with a negative sign, but yeah. So it'll be exothermiation for sure. Makes sense, right? I think. Does it make sense? All right. So I'll just stop here today.